ever knew. Well, here comes another picture of the atom, and that is given by Rutherford, a very famous scientist who worked in the 19th century in England. In fact, he was so famous that there is a research laboratory in England in his name. And I was fortunate enough to work in that lab for about 2 years. Now, a lot of work on atoms and the structure of the atoms, the structure of elementary particles are all worked out in that lab. Well, what did Rutherford do? Let me take you through an experiment that he did. In 1909, Rutherford arranged a sample of polonium. You see, before the advent of the study of the structure of atom, it was known that some materials emit deadly radiations. Polonium is a radioactive material, and it was known that if you have a sample of polonium in a box like this, deadly radiations like alpha particles. Alpha particles are actually made up of minute atoms. In fact, the substance polonium will emit these alpha particles with a tremendous velocity. Now, if you now want to know what an atom is made of, you know what scientists do when you want to know what an atom is made of? Well, what they do is keep a substance over there and bombard it with bullets. Alright? Now, what kind of bullets are they going to use to smash an atom? An atom is a very small object. So, if you want to smash or hit an atom, you need to use bullets that are very small. You can't use the kind of bullets we use in our guns. And now, this alpha particle that is given off by this radioactive material polonium is a very, very suitable bullet. So what Rutherford did is, he used a sample of polonium which gives off these alpha particles. They are the bullets. And he aimed these bullets at a very thin foil of gold, so that these alpha particles could go and bombard atoms of gold. You see? And then he could find out the result of this bombardment. Now, this is what he did. This is the polonium sample which gives off the alpha particles. And this is the gold foil, and he kept a screen. You know, a screen, I told you about zinc sulfide, a fluorescent material. Now here, if you keep that fluorescent material here, any alpha particles that hit the gold, if it escapes the gold foil, you can detect it. Anytime an alpha particle falls on a fluorescent screen, it will produce a light, a flash. So when you see a flash, you know an alpha particle has hit it. So this is called the detector, the screen. So once again, look at the arrangement he made. This is the gun, the polonium sample, from where alpha particles are released. So the alpha particles are the bullets, and the gold foil is the target. Now, after hitting the gold atoms, these alpha particles were detected on the screen. And now, what did he actually observe? So the foil was surrounded by a luminescent zinc sulfide screen to detect where the alpha particles emerged after contacting the gold atoms. After hitting the gold atoms, where did these alpha particles go? That was his concern. Now, Rutherford observed many of the alpha particles went through the gold foil without suffering much deviation. Now, you would expect that when a bullet hits something, it will suffer deviations. Is that right? That's right. Now, what Rutherford observed is that these alpha particles, most of them didn't even know that they were going through the gold foil. They went through straight. But some of them showed some deviation. Now, Rutherford said it was almost as incredible as if you fired a 15. Now, what happened is, before I talk about this sentence, you see, most of the alpha particles went through the gold foil without any deviation. But he observed that once in a while an alpha particle bounced back, almost got reflected backward. But that is something very strange. You see, the only way a particle that is going forward can bounce back is that it hits something very hard. Is that right? If you hit something very soft, it will go through it without having much deviation. The only way it can deflect or deviate or to bounce back is that it hits something really hard. So this observation prompted Rutherford to say, this is his own sentence, it was almost as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you. Oh well, can you imagine that happen? Now, he fired these alpha particles on a very thin gold foil. And some of these alpha particles bounced back. Now, it looked like as though you fired a big cannonball onto a tissue paper and it bounced back. Well, this is actually what happened. Suppose these are the gold atoms, right? Most of the alpha particles did not show any deviation. They just went through the gold foil. Now, what does that suggest? That suggests that atoms of any substance are mostly made up of free space. An atom, most of an atom is really empty space. And that is the reason why these alpha particles did not encounter any obstacle. Most of them simply went through without any deviation. But once in a while, look at this, once in a while, one alpha particle got thrown back, almost thrown back. The only way that can happen is this alpha particle encountered something really hard. Now, let me see if I can show you an animation of this. Give me a second. Now, this is the gold foil. Can you see the gold foil there? Well, of course, it's been made very thick. And this is where the alpha particles are fired from the polonium samples. You can see the alpha particles going with tremendous speed and going through the gold atoms. And here is the zinc sulfide screen where the alpha particles can be detected. And if you notice, most of these alpha particles are going through the gold foil without suffering any deviation at all. But watch, once in a while, some of them encounter something very hard and gets deflected, almost they are thrown back. And Rutherford was more interested in this behavior. He was not interested in the normal behavior that the alpha particles went through. But he was interested in the behavior of some of these that showed great deflection. If you notice, there are varying degrees of deflection that you notice there. But some of them were very rare, encountered a very hard part of the atom, which then made it completely go back. Okay, so what does that mean? Now, Rutherford argued that the atom has a positive core. Now, Rutherford said, unlike what Thomson suggested that the positive part is all distributed in a great mass and the negative electrons are distributed. Now, Rutherford said, no, that is not possible. My experiment doesn't show that to me. He said the positive part of the atom actually form a central core of the atom. In fact, that is the hard part. It's a very small part, but it is very hard. So, Rutherford argued that the atom has a positive core, and he called that the nucleus. So, this dark dot that is here is the positive part, that is the nucleus. And when an alpha particle encounters that, it is then that the alpha particle is bounced almost back. So the nucleus, therefore, is a very hard part. And that means most of the mass of the atom is concentrated at the nucleus. You see? And most of the other parts of the atom is empty space. So, once again, what did Rutherford say? He argued that the atom has a positive core called the nucleus, which is responsible for the diffraction of the alpha particles in that particular way. Now, this is what happened. If this is the nucleus, and alpha particles coming towards the nucleus suffers a considerable deviation. Now, apparently, alpha particles also carry a positive charge. So, when the alpha particles come towards the positive nucleus, the electrical repulsion just throws them away. Now, soon he came up with a new atomic model based on the results of this experiment. So, we are now going to look at the atom model put forward by Rutherford based on his famous gold foil experiment. I would like you to remember some of the details of these experiments. So, what is the Rutherford's model?